Thank you for coming. Try to keep this on time so that we can get everyone out to lunch. What I'd like to do is just do a quick check on some questions and see if I can kind of gauge some of the interest in different areas and knowledge. So how many people here today have used a virtual machine or at least know what a virtual machine is? Excellent, excellent. I was a little worried abbreviating VM that might throw some people. How many people here today have no need to store data persistently for retrieval? Oh, we got one. That was kind of a trick. Yeah, it was a trick question. It was a trick question. I was going to suggest if you know, you might want to look at dev null for your data storage needs then. But and here's a more serious question though. How many people here today have lost data due to either hardware or software failure or flaws? Okay, I apologize for your data loss because I'm one of those folks that, you know, over the years have been involved in the data path. So I'm sorry for your loss. And as always, have a good backup. I don't know if that would come across well in Australia or not. Joke is that everyone loves bacon, right? So everyone loves data. Okay, kind of fell flat, but that's fine. I don't know. It's a good friend of mine back in the United States. He's a vegetarian. He works in information technology, and he wears that shirt all the time. So, but on a more serious note, you know, without data, without persistence, without integrity, most of us wouldn't, you know, use a computing device of any type. I don't think anyone here would use an operating system or file system that would occasionally lose or corrupt data, at least not knowingly. So for the most part, file systems and the storage and the layers below it have to be very well written. They have to be robust and correct in the presence of errors. So testing storage-related functionalities is a requirement. It's imperative for functionality. And when I mentioned, you know, working in the presence of errors, that implies that you also need to test in the presence of errors. And that can be difficult when you come to hardware, right? You have a hardware device that's storing your data, and you want to test errors that might come out of that hardware device. That can be problematic, as you could expect. So I'm just going to do some quick, couple of quick slides here for just some background to make sure everybody, we're all speaking the same things. So in the context of this talk, when I say block storage device or block device, I'm just talking about what you'd kind of expect is a randomly accessible fixed size block device. The thing that you put a file system on. It is possible to run some file systems without blocks. Found out recently when I was talking to Dave Chinner on XFS that, yeah, we don't need blocks anymore. We can work with byte addressable memory. So that's something you can consider when you are selecting your file systems. And I might use the term logical block address. That is simply an abstraction that you use when you're using the interface. So logical block 0 is the first block on the storage device. Where it physically resides on the device is dependent upon the firmware and hardware. Just so you're aware of the terminology. And we're also going to be talking about errors today and how the errors emanate from hardware. So I'm going to give an example of the small computer systems interface, typically referred to as SCSI. So basically the operating system, you know, issues a command. We're going to keep it simple and say a read or a write. The initiator terminology is what you use kind of in the SCSI itself. The host side is called the initiator. The storage device is called the target. I'll try to be consistent today with when I reference those. So the operating system issues a command. Target receives a command. Target processes a command. Target replies with the status. Operating system, you know, checks the status and says, is it successful if it's error. In terms of SCSI, if it's an error, he will then immediately turn around and send a request sense command. And as part of that process, you can get additional information about what went wrong. In the case of a media error, which would be an 031101, you can get the logical block address that was reported in error. So you might issue a logical block read from 0 to 512 blocks in length, and it can tell you that block 128 failed, and I was unable to recover your data. I'm so sorry. So what types of errors might we encounter with a piece of storage? Most are probably familiar with temporary or persistent read or write errors. Actually, probably not so much on write errors, but on the read error path. There's a specific type of read error that you can get that can be corrected with a write, and I'll elaborate that just a little bit. I'm sorry?
Not always.
Not always. We'll talk about that too. There's temporary or persistent timeouts, right? Just failure for the device to respond to the operating system's commands. And just to give a little bit of background, I've been working with storage probably about 75% of my career for the last 20 plus years. And I had the privilege of working on disk drives, firmware, and test very early in my career. And this really surprised me. When I came into the industry working for the company, and I was like, and somebody said, oh, you know that a timeout can be worse than just not giving them their data, right? And I was like, what? That didn't make sense to me. And the reason for that is if you're providing enterprise storage, timing out is worse than just saying, sorry, I don't have your data. And the reason for that is you're typically running a RAID, right? It's better to just say, quickly, I don't have your data. There's other things that can happen, unexpected resets. So in that case, the operating system or initiator issues a command, and they get a check condition. They do a request sense, and the sense data says, device in the process of becoming ready. And that's when the operating system goes, oh, the device just rebooted itself. I'll have to wait. And you can do testing at readies and stuff to test where it's at. Some operating system functionality can detect incorrect data. If people have attended the ZFS file system talks, or if you use a file system like XFS, they use checksums on the metadata so that you can be aware that you just read something off of the media, you checked its validity and found that it was incorrect. At that point, you know that what you got back was incorrect, and you can, giving whatever file system you have, you might be able to fix it, you might not. Other things that you might encounter is high latency followed with poor performance. A lot of times, the two are related. If you're experiencing poor performance, it could be that the device is having problems. So to back up a little bit by the read error corrected by write, that is a specific case. It doesn't happen very often. And what it is you were in the process of writing a sector, you lost power. So they call it a torn sector because half of the sector, or some percentage of it, has new data, the rest of the sector has the old data, okay? So what happens is that when a disk drive is reading the bits off of the media, it is checking the data with a CRC, and it also has a certain number of ECC bytes. Most of this is done in hardware, or at least it was 20 years ago, so I'm guessing they're still doing the same thing. So in that case, you issue the read, you get an error. You can read it all day long for weeks on end, it's always just going to return an error. However, if you turn around and write the sector and read it, you'll find that it's working fine. Now in some cases, if you have an actual real media error and there's a physical defect, I used to call them thermal asperities, which is an interesting term, you can't. The block is bad. And there are SCSI commands that help you correct that situation. You can do a reassign blocks command. So you can take that logical block address and change its physical location so that you pick a new piece of media. No, you don't agree?
No, Western Digital.
I'm sorry?
I'm with Western Digital.
Okay, go ahead. What's your question?
In that case, if you rewrite either the right goes really in place, and so back to the previous case, if the sector cannot be rewritten, it's going to be remapped. So you keep your logical address as is, and the right will
Yes, there's mode page configurations from what I remember from my distant history. Like,
by default, it will do that. So there are commands there where you can tweak that.
yeah, yeah.
By default,
All right. So for the purpose of the talk, I'm not going to be able to repeat everything he just said, unfortunately. But if you want to look into auto write reallocation on error or auto reallocation on read error, check the SCSI documentation for those types of things, and I think you'll get some information. Excuse me?
Smart data gives you.
Okay, smart self-monitoring analysis and reporting technology. I think that's the right. Okay. And then also to get back on the poor performance. So when we get into this case where you issue a command, the actuator moves to the track of interest, waits for the media to rotate under the head, and you start doing the read, and you fail the checks, right? So the CR fails. You're like, now what do you do? Typically, then you go through some kind of recovery, and it might have one or more steps. Typically, it probably has many steps. So when you go through these many steps, you're going to take one or more revs. You're going to do different recovery techniques, which vary from vendor to vendor. They could be reading slightly off track. They could be changing channel parameters, tweaking all these different hardware parameters in hopes of getting their data back. Okay, so all that's going on, the initiator's just waiting. So that's where you can get the performance problems. You get longer. So in the case of where they actually do recover the data, then it'll go on and complete the rest of the transfer. Okay. So the importance of testing the storage stack. Obviously, if you have an operating system that's up and running, you're talking to your storage device and it throws an error, you need to be able to handle that, right? You don't want your kernel to crash and burn and take the system out. You want to be able to exercise those error paths so you can check, ensure data integrity, appropriate logging for the error that might have occurred. No memory leaks. Does everyone know what a memory leak is? Okay, good. Or correct behavior. So if you're doing RAID, you correctly return the rebuilt data based off the parity. So layering of the Linux storage stack. So where you generate an error basically dictates what in all layers might be involved in the Linux storage stack. And a good question might be, what does the internal architecture of the storage stack look like? And then if people are familiar with LVM and device mapper, another question could be posed of, how does the arbitrary stacking of device mapper targets on top of each other affect that as well, right? If people are familiar with like dm-crypt and some of the other device mapper targets, you can have quite an intricate stack. So here's, it's not super current. This is 4.10, so it's kind of old, but it's the latest one I could find. And I know it's an eye chart and that you really can't look at it very well from where you're at. But basically in the bottom you have the physical devices, and the top you have the file systems, the virtual file system layer, block layer, SCSI mid layer, and a bunch of stuff scattered in between. So in a nutshell, it's complicated. There's a lot of code in there. Does anyone have an idea, for example, of how many lines of code are in the XFS file system? Anyone?
I think at the moment it's about 50,000 to 80,000. I'm not sure because my last measure was almost 10 years ago. That's the problem.
Okay, well, I just recently checked on the 5.4 branch, and it's almost 100,000 lines of code in the kernel. So there's a lot of code. There's a lot of code in there. So some of the difficulties in testing are, the disk drive companies, they work really, really hard to make sure that they don't lose your data, and that's a good thing, very good thing. So if you have something that's really reliable and you're trying to write an operating system, how are you going to test it? How are you going to test these error paths? And that's kind of the main point of this talk today. These are some bit error rates that are advertised. I'm not going to point any fingers at any vendor. I think this is pretty consistent for different vendors. But I will point out the fact that if you Google CERN data integrity, you'll find out that what they actually experience is a little bit less than what gets advertised.
So you got the first sentence wrong, that's why. It's not one sector per 10 to the power of 16 bits, it's a bit error.
Well, I took this out of somebody's documentation, and they quoted it as sectors instead of bits, but
So
that.
when you go down to sector, yeah, you get it.
Okay. But just to kind of wrap up on the CERN stuff, they found 3 different categories of errors. Single bit errors that somehow ECC let through. They had sector or page size aligned corruption. And then in some cases, they had really big chunks of corruption, which they attributed to a RAID adapter and some drives that were falling out during RAID operations. So how do we effectively test error paths in an operating system? Before we totally do the reveal on that, some of the things that are desirable from error testing is just availability. Like, can everyone that wants to do this have access to it? Is it easy to use? Can you have repeatability? Low or zero cost, right? Some people don't have infinite budgets. And then ideally, a simple API to allow people to automate tests. So some different approaches. One approach, which is used a lot, is to fake it. And we'll talk about that a little bit more in some slides, and then some actual errors, which we'll get to as well. So here's just some of the ones I'm going to talk about today, just very briefly, to let people know that they exist and kind of what they can do. So a lot of times you have kernel developers, they're working on kernel software, and they might be working on software RAID, they might be working on LVM and device mapper, maybe they're working on ZFS. So they want to be able to test that, hey, when the sector is an error or some other error condition occurs, that they can handle it. So it's very explainable that a lot of these solutions are in the kernel, right? They know how to write kernel code, hence they write kernel code. So that's what a lot of them are. There's also a network block device, which can inject and return errors as well. We'll talk about that. So SCSI Debug, I've used this one a few times. It's a loadable kernel module. You can just load it up, and you can create one or more SCSI devices. It's all RAM-backed, and it has quite a few options. It's actually pretty full-featured. And you could put a file system on this, or you could layer it under a device mapper, and you could do some pretty good testing with it. Device mapper. So device mapper is the in-kernel component of LVM. I think I kind of mentioned that a little bit earlier. But basically, it maps physical devices into higher-level virtual block devices at a real high level of I don't want to get into all the details of its implementation and what it can actually do. But the device mapper community have come up with targets which can do things to inject errors. So dm-flakey, basically, it can allow your device to show good behavior followed by bad behavior, and there's some configuration into that. dm-delay, it's a target that allows you to inject arbitrary amounts of delay for measuring performance. You might want to play with that when you're using, for example, dm cache functionality to see how well that helps. And then more recently, some of the folks that are working on VDO, I don't know if you've heard of that. It's Red Hat's deduplication and compression technology that I believe is available in RHEL 8. Some of the developers worked on a target to simulate torn write, because they actually had a physical device that experienced that. They wanted to be able to test that scenario. Device mapper, it's interesting. You can talk to it without using LVM. There's a tool called DM Setup. It also has an ioctl interface and library that you can use. So if you want to write tools to talk to it, you can. Network block device. So basically, it's your typical client-server architecture. I've used this one to simulate a jump drive being pulled out while something's in use. We had I did some work on the Stratus project where a customer plugged in a jump drive, created a file system on it, and then they immediately proceeded to just yank it out. It was a good test because it crashed our user space daemon, and I wanted to be able to reproduce that in a continuous integration situation. And I found that network block device, you could establish a block device, and you could basically detach it dynamically. It allowed you to do that. So you could simulate a device really going horribly wrong. It has some really interesting features like sparse support. So you can create devices that look like 8 exabytes. I watched a talk by one of the developers, and it was very interesting when you take an 8 exabyte device and you try to create a file system on it. Some you can actually do, some you can't, because they write so much metadata you'd need, literally terabytes of disk space just to write the metadata for the file system. Errors, it can do read and write delays. There's some knobs in there to do percentages and probabilities as well. So it's pretty flexible. SCSI fault injector. So this one I haven't used, but I'm bringing it up just because it's an interesting approach. How many people are familiar with system tap? Okay, we got a few people. I'll try to give an executive summary. Think of it as its own programming language that can do certain logic with some publicly available symbols in the kernel that you can compile and insert into a running kernel while it's going. So you can do instrumentation, you can do some pretty cool stuff with it. So they took that, and then they combined it with a user space program which maintains state and dictates actions, and they were able to force the kernel down error paths. The project has been around for a while, but it kind of looks like it's stalled based on their site. But I found that it was pretty interesting. There's a good white paper reference there that you can take a look at. And the other interesting thing is they found a few bugs, real issues. I think it was in the multi-disk MD RAID. So it was very fruitful. So this is something that I used to do 20 plus years ago when I was fresh out of college writing test cases. SCSI allows you to do a thing called a read long and a write long. And so basically you can read up some of those extra bytes on disk. You can perturb them in memory, write them back to the disk, and then when you try to read it, you get a realistic failure. And this one is correctable if you do a simple write, because you'll correct those ECC and CRC bytes. I won't go into all the details, but if you're interested, don't do this on a drive value. These are some of the things that I try to remember from my past, but if you start mucking with sectors, the drive's going to start keeping track of stuff, and you might get auto reallocations that you weren't intending. You might get smart errors. The device might just say, "Hey, you've totally exceeded the G list, the grown defect list. I'm sorry, we can't do any more." So you don't want to do this unless you really don't care about the drive. But it is kind of cool because you can create very realistic errors. However, the errors are limited to read errors, which are pretty common if you're going to get an error. And this is what I used to do when I was a junior developer a long time ago. People that are paying attention might think, well, if you can read all those extra bits, well, I guess I didn't tell the missing part. You can tell the drive whether or not to apply error recovery before you fetch those bits. Whether or not they actually do it, I don't know. If most disk drive companies would probably hide their raw bit error rate, I'm guessing. I don't know. So main purpose of this talk, and the reason I'm here today, kind of excited to talk about this, is, hey, we're already simulating the world. Can't we just simulate realistic errors too? I guess for me, it seems like the holy grail of testing storage. Just have the device models and hardware return those errors. That's what we're going to talk about a little bit more. So what are the benefits of doing this? All those other solutions I talked about, you kind of need the kernel up and running. You need a loaded kernel module. You need to have the user space up. You need to have the network up. You need to be able to talk to things. If you do this in a virtual machine, you can present errors before anything happens, before you've even booted. You could test grub, for example. Does your solution that provides RAID work in the presence of errors at boot? It's operating system agnostic. I know we're at a Linux development conference, but we have friends here from FreeBSD and others that they might want to test their storage too. Because we're basically at the lowest level of hardware, you get to exercise more layers of the storage stack. but I do have a little note there that you know, the virtual machine environment has limited number of device models, host bus adapter models, so you can't test everything. If you're one of the lucky hardware companies where your host bus adapter is modeled in software, you get the added bonus that you can test your device driver as well. And then additionally, you're not consuming any resources from the guest OS. I mean, you are on the host, but from the guest perspective, it's all transparent. You can't see any of it. All right. So no artificial test code in the kernel, so you can test just like you would in production. Anybody who can spin up your virtual machine can do tests, and then we can create errors for all the different supported device types, attachment ops, and protocols. So it's pretty flexible. All right, so what could possibly go wrong with this approach? Mimicking hardware. Sometimes hardware gets it wrong too. If you look in the Linux kernel, there's code in there that handles hardware problems. Vendors have shipped products that violate protocols. So if we're doing this in a virtualized environment, we want to make sure that we're doing it correctly. So that's something we really have to be aware of. We don't want people to start using a tool like this, writing code, and then find out that it doesn't match reality. That would not be helpful or useful. The other thing that was interesting when I was talking with the QEMU folks is that they accurately reflect all operation, including bugs. So they're bug-for-bug hardware compatibility in their models. And they have to do that because if you're going to boot an operating system with a device driver for that piece of hardware, it has to function exactly like the hardware, bugs and all. So some other potential things that we could do once we start snooping around in the device models on a virtual machine is we can gather statistics. I'm sure some of the people in this room are familiar with block trace. It's kind of a cool way to figure out what's going on in your block layer. And when you have that type of data, you can start looking at histograms and gather all kinds of data about what your file system is doing, what your application is doing. And now we have it in a way that's operating system agnostic if you want to do some kind of comparisons. There's actually, I'm not sure if it's a filter driver or what the correct verbiage I should be referring to in QEMU, but they actually have some functionality where they will capture the sequence of commands. And I believe it's used to do backwards execution of the virtual machine for bugs. So you're running forward and you hit an error, you can roll everything backwards to get back to where it went off the rails and started going wrong. I believe that's what it's for. Hopefully I'm correct on that. And of course, you can do some repeatability for reproduction analysis. Future ideas. So when I created the slide a few months ago, I was thinking, the disk drive companies have been working on shingled magnetic recording for quite some time. I noticed the Western Digital signs out there with a nice link to a website. Yep. I want to talk to you later after the talk. And it's all about shingled magnetic recording. It's an interesting technology. And when I was thinking about the virtual machine and like what things could we do, I was thinking, wouldn't it be great if we had a device model that functioned like a shingled magnetic recording drive? Now you can have device mapper developers working on functionality. You can have file systems, and anyone could be playing around with it. And I thought that would be a good idea. I think Western Digital has ability for people to do that. It's not, yeah. So, but it's not. I don't know. I don't know the details of it. So we'll have to look into that. And then obviously expanding the device models and making them act more like real hardware. That would be useful. So what I did, whoops. Oh, technical difficulties. Hang on a second. Okay, I'm caught up. What I did is I grabbed the QEMU source code and I started modifying it. Oops, I'm one slide ahead, sorry. There's the GitHub repo. What I did is I added a QAPI, which is a socket-based interface. for adding and removing media errors for one or more block devices. It's pretty simple. It doesn't do a whole lot. I made modifications to SCSI, HCI, and NVMe block devices. And I also put in functionality so when you issue a command, say the starting block and a transfer length, that I can tell you which block in the transfer is the one that got the error. And I modified the SCSI path so that we return accurate sense data with this sector in error. If I did it right, that's still need to validate that. So I did all this work. I posted the patches upstream, and then the QEMU developers were like, we already do some of this, dude. They have a thing called block debug. It utilizes a configuration file, so it's kind of static. You create a file, you reference it in your QEMU configuration, and it gets read up when you start the virtual machine. It does have some really cool logic that you can have states. So it's like, hey, when this happens, then wait for this to happen. So you can do timing type activities, which might be very fast. So that's kind of interesting. Obviously, I wasn't aware of this when I started my other work. Otherwise, I probably would have done things differently. But to the credit of the QEMU upstream community, they were very, very nice to me, and they didn't do any public shaming or anything. So I give them credit for that. The plan is that I would like to integrate some of the features that I added with the existing functionality and merging the two together, so it's kind of like one area of the source code base. I would still like to see the QAPI because I think it's nice to be able to dynamically change the state of the virtual machine while it's running. I think that's important. So why did I do all this? This was kind of a pet project of mine. I've been working on a problem internally at Red Hat that I went public with just before the holidays on the Linux kernel. So today, when you get a print K message from a storage device like, hey, some sector had an error, it's on device SDA, which physical device is that? And some folks in the room might understand that every time you reboot or dynamically change your hardware configuration, your device nodes change. So those identifiers are not very useful when you're looking at historical log entry data. So what I did is, using the changes that I did in QEMU and creating errors, forcing the kernel down some really interesting error paths, I modified those code paths to include the VPD83. It's a vital product data. It's available on a number of different devices. And that gets tagged with the kernel message. The kernel messages have an ability to have structured data, key value pairs attached to a log message. And the beauty of that is that when you do it, you can use journal control. You can say key equal value, and it's wonderful. You now get a consistent picture of all the log messages for that device over your entire history. We're still kind of working on the details. I'm still trying to work on some buy-in in the upstream community. But I'm hoping that we can come up with some kind of solution where we can provide that functionality to users, because I think it's important. So what else can we test with a virtual machine? And this is an open-ended question to you guys. I know that there's other virtualized environments that can do latency on networks, error, lost packets. I'm not sure if persistent byte addressable memory devices are available in virtualized machines. And when I was standing in line for registration, one of the other people that was attending that I was talking to was like, hey, we used to work on FTL layers. How about like an MTD device? And that actually exists. I did a little research on that. That's available. So that's all that I have. We got some time for questions. So go ahead.
Can you also configure for incorrect sense data in your system? So typically the drive would not return incorrect sense data for any error, but HBAs, my God, that's a nightmare. Especially if behind your SAS HBA it's a SATA drive and they have to do some sort of translation, generating the sense data. It's a nightmare. It's buggy. It's horrible. And so you very often, that's my fight, you get an error for your I/O on the kernel, and the sense code is unknown, or it's just completely out there and doesn't make any sense because it was badly translated by the HBA. So the response to the error by the kernel is wrong, which can ripple effect and go bad in
So you're
all
just
sorts
asking
of
the
ways.
question, what I've provided, can you create incorrect sense data in response to an error? And the answer right now is no. Okay, good to know. If you want to hop on the QEMU mailing list, we would welcome your comments for future improvements. It's very doable. There's no reason we can't do that. So yeah, any other questions?
I also would have a suggestion, missed interrupts and spurious interrupts. So you submit something, a block request, and then you get no answer for forever. And leading to hangs and so on. And these are very scary for higher layers.
So you're basically asking, can we add support for
Yes.
devices that time out, don't respond?
Yes,
Drop
timeout,
the command and forget that they ever got it. Yeah, we could do that. That's not a problem.
So that was very fine for certain cases for testing.
My hope is that if we can get some upstream adoption and get some work included, I would like to see this include all kinds of errors, media errors, timeouts. I would also like to be able to do error injection of the user data so that you can simulate bit rot, so that you can test ZFS and ButterFS to make sure that they're actually checking their checksums correctly and you're detecting the errors so that your data is actually safe.
Hi, thank you. So if you wanted to do these tests rather than on virtual machines because you've got hardware that has space, but on a cloud provider where you don't get access to the host machine or the underlying QEMU, what would you recommend? Would you suggest that maybe doing those earlier things that you were listing, writing to dev devices or proc or whatever to test if that was the environment you were operating in?
Yes, exactly. In those cases, if you don't have access to the virtualized environment because you're executing on a cloud, you have no choice. You'll need to do something in kernel. And there's nothing wrong with the in-kernel stuff. People are using that today, and they're using it very effectively. I'm just kind of advocating that if we add this functionality to the virtual machine, we can get some additional added benefits as well. But there's a ton of test code out there that's using existing testing mechanisms, and they're being very successful with it.
Hi, thank you for the talk very much. I'd also like to echo the earlier suggestion in terms of timeouts for errors, and I'd like to add another suggestion in terms of being able to simulate misdirected reads and misdirected writes.
Yes. Yeah. Neighbor tracks. For example, neighbor tracks. So accidentally the hardware is overwriting not the correct track, but the neighbor track.
So
classical problem.
Yep.
You're basically saying, hey, I want to write to LBA 100, but can you point it off to LBA like 768 and step on something else?
Yep.
That would be a gross drive hardware problem.
But it's easy to trigger. You just check your drive while operating.
That's the old
We have another question over here, please.
Thank you. Are there specific flash drive failure modes that would be, we've all had them in the past, rather than, I'm wondering whether the failure modes are really just basic, you're still going to get corrupted data one way or the other. Are there particular modes for flash drives that are different?
I don't have a good background in Flash, so I really can't answer that well. But any device that stores data has the capability of not returning your data. It has the ability of corrupting your data. I mean, all of these things can happen on any device, right? So I think in general, as developers, we need to be aware that what's protected and what isn't protected. We know that XFS protects itself, but it doesn't protect your data, your user data. So it's very important that if you're a developer and you want your data files to have integrity, that you do the due diligence to make sure that you're checksumming your own files so that you can tell your users that something bad had happened. It's not ideal, but that's why file systems like ZFS and Btrfs exist, because they have that functionality. Next question.
I do have a background in flash drives. I think a lot of the weirder particular to flash errors that we've seen aren't particularly useful to reproduce because there is absolutely nothing to be done about them. You may as well, they're silent failures. For example, there was the bug a lot of drives had where if you cut power in the middle of the write of what they call the find write for second level, for 2-level storage, it would also wipe out the entire block for the first storage. So you would randomly lose 1 megabyte of data. And that was 1 megabyte that was consecutive on the flash, but of course that would be scattered throughout your file system. So you would your file system has now randomly lost 1 megabyte of data. There's not much point simulating that because there's nothing to be done about it.
Yeah, I think in those cases, being able to inject, data corruption to validate, file systems and applications is useful, and also being able to, timeouts and other errors, I think is useful. But yeah, I don't think, from a flash standpoint, you really have anything else that you can, benefit from.
Yeah, so just to continue on for that, you're right in terms of if you have a single drive and you're simulating those sorts of failures, there isn't too much that the file system can do. But if you're dealing with, say, multiple drives and you're trying to simulate an array, sorry, a RAID array or a erasure encoding system or something like that, being able to simulate those failures is very useful.
I think possibly we've got time for maybe just 1 or 2 more questions.
One suggestion, data integrity is an option. So in hardware, you have more than 512 byte sectors, some additional bits in order checksums and so on. And if this could be simulated, it would also be an addition, I think. But it's rarely used.
That's just an internal,
Yeah.
It's a feature of the hardware to make sure that it's returning correct data to you. And I don't know.
No, the driver gets there's a mode where you can get the bytes and can inspect them.
There's a thing called diff and dix. I would suggest you Google for it. And the idea is that you attach a 4-byte CRC to your LBA.
Yeah.
And if you have the correct hardware support, you can carry that data integrity up through your hardware until it gets to the operating system.
Yeah,
so if it's really important to you, there are hardware solutions that can help you gain extra data integrity at the block level like that.
Quick one. Any thought on integrating into BLK tests?
I'm sorry, repeat that?
Integrating this solution in block tests, BLK tests. It's not a file system, it's really block layer specific tests. But it's around and it's heavily used, so.
None of this has been integrated upstream. I still need to do a lot of work to massage it and get it to work with block debug. But I'm hoping that, once it's in there and it's upstream and it's shipping, I hope people use it. I mean, that's my intention.
Okay, I think we're just about out of time. It's lunch.
All right, thank you, everyone.
Tony,